Welcome back to Honors Calculus. In this video, I want to look at integration by substitution. In previous videos, we've started to build up a library of rules for performing integrals, performing antiderivatives, by looking at the rules we have for differentiation and kind of turning them on their head. We've seen that the linearity, the power rule, and the rules for trigonometry translate fairly nicely. In this video, I want to focus on the chain rule. Remember that for differentiation, the chain rule tells us that the derivative of the composition f of u of x is f prime of u of x times u prime of x. And so if I integrate both sides of this equation, I will get the integral of the derivative, and by the fundamental theorem of calculus, the integral of a derivative is the thing you started with. So f of u of x is equal to the integral of f prime of u of x times u prime of x times dx. And that is the rule for integration by substitution. That's what we're talking about when we say substitution. Although, to make it make a little bit more sense, we tend to clean this up. And instead of trying to deal with it as this form, we use what's called a change of variables. And we'll write that du is u prime of x dx. And then my integral is just the integral of f prime of u du. And with that, we turn this rule directly into the fundamental theorem of calculus. So that's what we mean when we say a change of variables, and that's the notation that we typically use when we talk about the method of substitution. And because the variable u is far and away the most commonly used tool here, we will generally refer to it as a u substitution. But it's the method of substitution by change of variables to use the chain rule, right? With the theory in our pockets now, let me get my head out of the way, and let's take a look at how this works. For example, let's look at a fairly simple example to start off with. How about the integral of the square root of 3x plus 5 dx? We have the ability to integrate the square root of x, but we don't have the ability to integrate a square root that is more involved in what we've done before. But from what we've seen working with the derivative and the chain rule, hopefully at this point it's almost second nature that you can look at this and say, oh, this is a composition of two functions. We are taking the square root, and the thing we're taking the square root of is a function. Right? So we will write out a substitution. Let u equal 3x plus 5. And then we will differentiate. The derivative of 3x plus 5 is 3. And we're suppressing some of the notation compared to what we did on the earlier slide, but this is u of x, and then du equals u prime of x dx. Right, so u prime in this case is just 3. All right, so we're just taking a derivative, we're writing it using the differentials that we talked about very briefly, and we're able to go from there. All right, but figuring out that 3 is the last challenge in this problem. because we don't have a 3 sitting there. We just have the square root of 3x plus 5 dx. So we're going to use mathematicians' favorite tool. Look at something that's not there and force it to be there. I need there to be a 3 here. I can't just arbitrarily put a 3 there, but I need there to be a 3 there. Well, if I also put in a 1/3, 1/3 times 3 is 1, and by doing that, I haven't changed anything at all. And now I've got 3 dx, and I've got 3x plus 5. And so I can perform my substitution and rewrite this as 1/3 times the integral of the square root of u du. This integral now suddenly has become something that is very straightforward. I know how to integrate the square root of u. That's the same thing as u to the 1/2 power. And by using the power rule, 1/2 plus 1 is 3/2. And technically that 1/3 should multiply the c as well, but c is an arbitrary constant, and 1/3 of an arbitrary constant can still take on whatever value you want it to take on. So we'll be lazy and leave that out. All right, cleaning up my coefficients here, 1/3 times 1/3/2 is 1/3 times 2/3, which is 2/9. And then u is 3x plus 5. I'm going to go ahead at this point and substitute that back in. And call it 2/9 times the quantity 3x plus 5 to the 3/2 power plus c. All right, and that's how we can use substitution in order to take an integral that is more complicated and rewrite it as something that's a little bit more straightforward. This particular integral we probably could have solved using a direct guess and check approach. We could have looked at that and said, oh, we're taking the square root of something. We're probably going to have that something to the 3/2 power using the power rule, and then played around guessing at the coefficients to come up with that 2/9. The next example is a little bit more difficult in that sense. The integral of x times the sine of 4x squared dx. In this particular integral, the first thing that I notice is that I have a product, right? I've got x and I've got sine of thing. And it turns out that that extra x is actually incredibly important for figuring out how to solve this problem. Without it, we wouldn't be able to do anything. But the most complicated thing that I have happening in this expression is that sine, because the argument of the sine is complicated. It's not just x. And so I look at that thing inside there and I say, well, let's see what happens if I let u equal 4x squared. Well, then that would mean that du has to be 8x dx. I've got the x, I've got the dx, I need the 8. I can use the same trick I used in the previous problem, rewrite that as 1/8 times 8, and now we see why we didn't have to worry about that x in front. Because when we went through and we found our substitution, we needed that x, right? The x out here has to be there, otherwise we can't find the derivative of the argument in order to complete the chain rule. But now that we have that, we'll have that 1/8 in front. Sine of, instead of 4x squared, I'm now calling it u. And then instead of 8x and dx, I'm calling all of that du. And I've turned this thing from a complicated integral to a very simple integral. right? The integral of sine is the negative of cosine. And I can substitute back in my last step. U is 4x squared. And once again, technically, yes, that 1/8 should be multiplied by our arbitrary constant c as well. But c is an arbitrary constant. It will take on whatever value we want it to take on. We don't have to get any more specific than that, right? Constant value multiplied times arbitrary constant is still arbitrary constant. It can still take on all real numbers. We don't have to worry about writing all those bits out. I do want to point out in this problem how important that factor of x really is. If I look at just the integral of the sine of 2x squared dx, well, following the rule that we've laid down, if I let u equal 2x squared, then I would get that du is 4x dx. And while it is perfectly reasonable for me to introduce a 4 and a 1/4, I can't introduce a 1 over x. If I tried, I wouldn't be able to bring it outside the integral, right? With a constant, I could bring that constant outside the integral, right? The integral of 1/8 times 8 times f of x dx is the same thing as 1/8 times the integral of 8 times f of x dx by the linearity rule. But with a variable, the integral of x times 1 over x times f of x dx, I can't bring that x, or I guess the 1 over x in this case, I can't bring it outside because it is itself a function of x. Right, so no further work is possible. I'm sorry. I thought I hit the button to make me go away, and it didn't make me go away. Right? If I have x times 1 over x to introduce that x that I need here, I can't bring the 1 over x outside of the integral because 1 over x is a function of x. There's nothing else I can do there. There's no further work possible. That's something that's frustratingly common with integrals. When it comes to trying to evaluate integrals by hand, it turns out that more often than not, the expression you're looking at is impossible to integrate analytically. And that's why we have numerical tools. That's why we have the Riemann sum and the limit and all of those other structures that we've looked at previously. For the purposes of calculus classes, we're going to stick to examples where we actually can perform the integration. It turns out that, shockingly, people have spent a lot of time investigating the types of expressions that tend to come up in applications. And so we will eventually get through, in the further semesters of calculus, rules for integrating a number of different problems and processes. But for right now, just the basic rules are going to get us through the rest of this course. All right. Let me wrap up with a problem for you to try. I'd like you to take a look at the integral of 2x squared times the square root of 1 minus x to the third power. All right. As with previous examples, it looks a little bit intimidating, but if you play around with substitution, you should find that it's not that difficult to work through. Take a few minutes, see where you get to with that, and I'll see you in the next video.